In the beginning of this section of the course, I showed you this tree of knowledge that looks like this, or maybe I should have called this a mountain of knowledge. And so far, we have learned about sine waves, we've learned about complex numbers, and we've learned about the dot product. And what we're going to do now is start building on these elementary concepts to create more complicated mathematical objects, and that's going to work our way up towards the ultimate goal, which is to learn about Fourier coefficients. And so in this video, we are going to discuss complex sine waves. The good part is that there's nothing really terribly new in this video. Essentially what we are going to be doing is taking a sine wave and embedding them inside complex numbers. So let's have a look. Here we have the familiar Euler's formula, e to the I k equals cosine k plus I sine k, where e is the natural exponential, I is the imaginary operator, so the square root of -1. That's the same as this I here. And k is some angle. So now what we are going to do is replace k with a longer expression. So instead of k just being one number, just being an angle, k is going to be this entire expression, 2 pi ft plus theta. Now what's interesting about this extension is that here k is a single number, but here we are saying that k is actually a vector of numbers. It's a whole series of numbers because this t is a vector of time points. So therefore we can just rewrite this as, so this is CSW, this is complex sine wave, equals e to the I times all of this business, 2 pi ft plus theta. So you just have to be mindful that we are not putting the cosine or the sine into the exponent here. It's just the innards, the inside of the function cosine and the inside of the function sine. And that goes here, e to the I, instead of k, 2 pi ft plus theta. So what does this thing look like? What does a complex sine wave look like? Well, here we have a real part of a sine wave, so a cosine. So this is y equals cosine 2 pi ft. And then here we have two parts of the complex sine wave, so the cosine part and the sine part, and I'm plotting them both on the same graph so you can see them. So they're both sine waves, and one is shifted from the other. And how much are they shifted from each other? You guessed it, it's pi over 2. They are shifted by pi over 2 because that is the relationship between cosine and sine. So cosine and sine are basically the same function, just shifted by pi over 2 or 90 degrees. So this is one way to look at a complex sine wave, where we're taking a two-dimensional axis and plotting both the cosine part, so the real part, and the imaginary part, the sine part, together overlaid on the same plot. However, this is not really the best way to plot a complex sine wave, and that's because a complex sine wave is not two-dimensional. This is a two-dimensional plot, but this object, this complex sine wave, is actually a three-dimensional object. What are the three dimensions? Well, we have time, that's given by this vector t. We have the real part, which is the cosine, and then the third dimension is the imaginary part, which is given by this sine. So therefore, the best way to conceptualize and to visualize a complex sine wave is something like this. So we have a three-dimensional plot. So we have time on the x-axis, the real part on the y-axis, and the imaginary part on the z-axis. So you can imagine this is like a slinky, like a corkscrew. So it starts off here, and then it's moving through time. As time increases, this complex sine wave is spinning around and around. So this is really the best way to visualize a complex sine wave. And the final thing I would like to mention in this video is that typically when working with complex sine waves, we leave the phase out. So we set the phase implicitly to 0. And so here I wrote 2 pi ft plus theta, but you can see that if you just set theta to be 0, then this shortens to e to the I 2 pi ft. And that's also what I've written here, and here, and here, and also here.